and semi-metal. And in such cases, the bonding metal to metal or metal to semi-metal takes on a partially metallic and partially covalent or ionic nature. We have already seen some years ago these, let me say, specific compounds which can be formed inside solid solutions when we talk about binary phase diagrams. And in that case, they are special compound having essentially bonding properties which are not fully metallic, but they are covalent. And the existence in these cases of a strong intraatomic bonding due to the gives as results in terms of macroscopic properties of the materials high elastic moduli of the materials itself, that is, they are to some extent stiffer materials than conventional one. Then the presence in the forces, for example, aluminum or silicon, can give to the bulk materials the capacity to form a protective surface layer, essentially when we are working in oxidizing environment, thus giving to the material itself a good oxidation and, generally speaking, corrosion resistance. So, having in mind this general concept, a considerable effort in the years has been reserved to the development of intermetallics as aerospace materials. But there are still some drawbacks, even though some niche application, as I told to you, they are still they are existing. And the problems is they have a good strength and a good environmental stability. They usually offer ductility and low toughness resistance and not a so good grip strength, as well as this concept, they are combined with increased, which have essentially hindered to a relevant extent the wide introduction of the intermetallics as industrial structural materials with a very wide applications. The family to which, for the purpose of our course, we must put our attention on aluminide alloys. This is also the intermetallic solution during the years up to today. I report to you just a very brief outline of the developments in this family in the past years, starting from the, let me say, discovery of the potential of titanium aluminide, which can be located near the 90 years. In this case, in this period, it was understood as it was possible to fabricate, with all the drawbacks, aluminide bulk materials made by one phase which is called alpha 2 and one phase which is called gamma phase, respectively. The first, alpha 2, made by the stoichiometric ratio between titanium and aluminum 3 to 1, And the second one, the gamma phase, characterized by the stoichiometric ratio 1:1. So this was the first evidence, let me say, about the possibility to fabricate materials. So the titanium aluminate. Then after the fourth experimental evidence, studies began on the role of addition of different elements to low percent value, so related to the overall amount of aluminum, for example, for the addition of manganese vanadium in order to balance the expected, the obtainable mechanical properties and the improvement expected improved in the chemical oxidation behavior. Moving on in the year 95, in this period it was developed the fourth generation alloys, which were based on the composition 42% chromium or manganese or other elements I mentioned before, being the balance in this way composition, obviously titanium. And with a reasonable compromise in terms of mechanical properties and oxidation resistance. And so there is a possibility to use these materials for the reasons that we will see later when we will at a glance the most important mechanical properties of the bulk material for the fabrication of turbocharged rotors or valves in automobile engines, or for example, both for the aerial field or the land-based field. First components fabricated the process and then solidification, thus starting also studies with the development of grain size distributions that, as you know, room temperature mechanical properties. And at the same time, to develop techniques for rolling, up to 2000s, the research activities were concentrated on two lines: on the development of very, let me say, specific technologies in order to reduce contaminant-free in production, because for these kind of materials, they can exhibit controlled composition. Impurities can represent a problem. And then on the development of more complex alloys, like for example the one which is reported on this slide, made by titanium, aluminum reduced up to 44%, combining in the composition a transition metal such as, for example, chromium, to control ductility, such as niobium, tantalum, etc., improve creep and oxidation resistance, obviously, and oxidation properties, And a semi-metal, such silicon, boron, carbon, again, used to improve the clean behavior of the materials. Having again in mind eventual additional problems due to the formation of segregation during cast, which again can affect material homogeneity and thus material. The attention was put also on the development of processing technologies for production of, again, more performing automobile builds by introducing also other techniques with respect to the one I have already cited, like, for example, extrusion, or, for example, that's very important, power metallurgy-based techniques, to which we will, on which we will spend some words at the end of this chapter. We can include also the isostatic pressing techniques. And so the attention was put on casting, powder metallurgy, extrusion, forging for the preparation, for example, of turbine blades. Then to fabricate components size was the main activity in that period, as well the beginning of the applied, that is not only on cells for welding by using friction welding, or by use of, for example, welding based on laser techniques, to transfer the possibility to use real engineering components as the components we have in mind during our discussions. Some other variants have been then developed in terms of composition, for example, by using niobium, and then they have been fabricated, and we will see later on, also very temperature turbine blades, by referring to this class of materials with specific techniques of power metallurgy based on hot isostatic pressing. Anyway, we should this titanium aluminide, the most performing is the gamma titanium aluminide, even though we can have a combination of alpha 2 and gamma phase. They are still relatively very young in terms of age of materials, because essentially in a practical way they have been more or less available. Have in mind that each single based superalloys, we can say that these nickel-based superalloys have been studied and optimized for more than 50 or less 60 years in production by titanium aluminides and gamma phase. They still are, as I said, young, and so they still need and request for a widespread potential possible application, further optimization work which must be done. Here you have a table just to give to you an idea on the two forms of titanium aluminide you see in the third column of the first table, alpha 2 phase, and in the fourth column of the table, the gamma phase. Some of the properties compared with nickel-based superalloys. Why we are going to compare with nickel-based superalloys? Because in our mind, we want to understand the possibility to replace in some section of in favor. This is quite interesting, and this is the reason because of the attention the scientific and technological community put on this family of metal to semi-metal materials, because if you see, first of all, the first line, density, we are talking about something in titanium aluminide, which is comparable in terms of density with titanium alloys, which is more or less half of the density of nickel-based superalloys. So this means that if we look only to density, we can expect light wave stiff value. These are the values of the young modulus. You see that they are, as I said before, with respect to titanium, stiff materials, which are going to approach, due to the number of gamma phase, 175 gigapascal, of the nickel-based superalloys, about 200 gigapascal. But if you divide the value of the stiffness by the density, and so you have the specific stiffness, which is an important parameter for us, just looking to these numbers, the gamma titanium aluminides can be considered as most performing than nickel-based superalloys. They do have also a respectable, if you compare with conventional titanium, resistance to high temperatures. If we are talking about creep resistance, or if we are talking about oxidation resistance, because see again the gamma phase titanium aluminum, we can expect something which is around 9 alloys. That's true, but it is sensibly higher than titanium alloys. And if you remember, when we had the possibility some years ago to discuss about the titanium alloys, we said, well, titanium alloys, they are pretty interesting metallic alloys because they are light than 45 grams per cubic centimeter. So they are lighter steels, for example. They do have titanium alloys than 600 Celsius. And so they can, in principle, just looking to these numbers, be proposed for high temperature applications. But at that time, we said that this is true, and apart from the possibility to have a better transition that depends on the alloy composition, the maximum working temperature of titanium alloys, even though they have one, is limited, we said, to value which are around 600 Celsius. And this was essentially and primarily due to the very low resistance to oxidation with an active oxidation, that is with an active mechanism of high temperature corrosion. But if we move to gamma titanium aluminides, we can achieve 900 Celsius. So it's more or less 200 less Celsius on titanium alloys. And so if we look to these figures, what we could say that for turbine blades, not only limiting, as it happens for conventional titanium alloys, for compressor blades. Obviously, we cannot propose to use these materials for four-stage blades of a turbine, where we still need the high resistant temperature of 1100 Celsius, which can be offered in the intermediate pressure stage or in the low pressure stage of an air engine. So the, let me say, drawbacks which must be managed in terms of technological processes, which are related, as you see, to